Hello, everyone. Today I'm trying to kind of make an analysis of a small project I've been working on last weekend. It's really a small, really small project, nothing fancy. It's more about me trying to understand how gated recurrent unit work and more in general recurrent neural networks. In this case, I just Googled for toy datasets for analyzing to train at least gated recurrent units, and I trained one on this adding problem. The adding problem is we can see it here, I guess. No, all right. Well, but it's really easy. It's a set of numbers. It's a set of couple of numbers. So you have, like, for example, 37 and 1, and then 21 and 0. And those numbers that are marked with the 1, meaning that they have kind of a flag saying true, those are added to the sum, and the neural network is going to see one element per time, one couple. So it will see, for example, 21 0, and will say, okay, this is flagged with 0, so it's not going to be added to the overall sum. The next element, it's 37 1, and that means that that is going to be added to the sum, and so on. So really quite easy. Architecture of the model is quite easy, really nothing fancy, nothing too weird. In this case, it's just GRU, so gated recurring unit, with input size 2, the couple of numbers, the number and the flag saying that it's going to be added or not. Hidden size, my case was one layer, so really easy, and one linear layer fully connected, connected obviously from hidden size to that is 1 to output size that is 1, so it's really one weight plus BS that is going to. Actually, it turned out that this was crucial, even though it's really one weight plus a BS parameter, so it's not really something too fancy. One would say that the hidden size would be enough. Turned out that it wasn't enough, like at all. Problem was that without the linear layer, the model was just learning the average of the distribution of the inputs. So, for example, if I put random numbers from 0 to 10, and there were like two of them with flag 1, it meant that in general, the average of a number, like the most, it was uniform distribution, so not Gaussian. It meant that each number was equally probable. So at the end, the average was like 10. So it kept saying 10 because it was distant enough from each and every sum in the training data. So this was crucial, and this is important because I'm doing a research project where I'm trying to have the smallest possible hidden layer, meaning that in my project I will need for sure the linear layer. I would need it anyways because my project I need to classify over 7 possible classes, so that was for sure that I needed some kind of linear layer, but even more now. Initialization, sorry about that. Initialization is done. I googled for this because I had no idea. And at the beginning, it was so frustrating because the network wasn't learning anything. Without this initialization, the network doesn't learn. It's really harder to much harder for the network to learn something. So really important to remember this. So let's go to the more important stuff. um, first of all, the training loss went down really fast. Around epoch number 100, we had the first like drop from 1 to 0.18, what it is. Then it plateaus. It's quite normal. It plateaus because we have employed in the training. Maybe it's here. I think so. Let me see. Should be here. I don't find it now. In the optimizer, we employed. Oh, here. We employed a reduced learning rate on plateau. This was also important because otherwise it would just go over local minima and it couldn't find anything better than that. And as you can see from the training loss function, training loss plot, this might be the case. So here it found something and it just dropped again and it was near zero. One would say that here is like the minimum, here goes to the minimum. It's not the case. It's not the case at all. We will see later in the weight dynamics over time that this was not the case at all. Like after epoch number 1000, it just kept changing a lot the weights, and since it's really precise now, the model, I guess that this was important. Now, this is the validation loss. Yeah, I need to make some fixes to the blog. I use the same function to plot them both, but here's the validation loss. You can see one really important thing to begin with, meaning that being that the validation loss goes hand in hand with the training loss, so it's really like a copy of it. One thing to keep in mind is this, because whereas in this case we had a loss that went from 1.2 to 0, here we go from 10,000 to around 0. The validation loss at the end was like 3 or 4. I don't remember now the numbers, but I think I will put the CSV in this document with all the data I have gathered. But yes, this is really important. As I said, this is important to observe because the model was overfit to the data. Then the analysis of the weight would have been nearly useless. So this is really, really important. The model did generalize, so we can study it and we can learn something about it. So here is a small starting point. So as I said, input layer had two values in the beginning. Each of the temporal sequence item had add a dimension 2, and obviously since we are using a gated recurrent unit, we are using 3 weights: one for the reset, one for the update, and one for the new gate. Here is like really quickly how the GRU works. Nothing new, nothing special. This is already something that we might look at. This is random initialization, so it doesn't make really much sense to look at it. Here we can see something already that is really important. We will see later something more about this, but first of all, Eden to Eden stays, it changes after this, but then it stays the same. So it's like blue, violet, yellow, blue, violet, yellow, blue, violet, yellow. So it doesn't change. It changes in magnitude, but they all change almost hand in hand. Not this one. You see here it changes by a magnitude of zero point 0.3, zero point 0.3, you see, 1.09, 1.13, so it doesn't change really like at all, almost. So from the start to the beginning, when started say epoch 750, it goes like 104, 109, and 113, so it doesn't change much. This goes from minus 0.84 to minus 0.64 to minus 0.14. Really important to remember the order of the weights. The first index 0 is the one that changes so much here, is the reset gate. The other two are the update gate and the new gate. So this says, how should I update the memory cell? Okay, so this says I have the value in my cell right now, and I need to update it to with the new value. How much weight should I put on the new value and the old value? This is the new gate, so it says, let's see here. So this is the new gate. It's used here in combination with the update gate. So we say how much of the new information I have gathered in this new round of calculation should I keep, and this is how much should I forget. Let's say this way. So this is nice to see, but doesn't say really much. Okay, so section 6 is really nothing more than more thorough explanation of the problem and how the GRU works. This again was more for me to understand better how they work. Here is some debug I will remove after the recording, I guess. So this is an input sequence I tried as an example through this article just to be sure that everything was working properly. So we see here that the output is 57.8, which is again the real sum almost when we approximate by the ceiling function. So you see here 12 0, so this doesn't go, this is not added to the sum. 37 1, this is added to the sum. 12 0, this is not added to the sum. 21 1, so 37 plus 21 is 58, which is actually the result we see here. So here's just really through the whole calculation around that sequence, which yields at the end 57.0809 and so on. This was just for fun, actually. This wasn't fun because obviously when you use PyTorch, you have everything done for you, so you don't encounter any really big issue. I encountered a really big issue I want to share. The big issue is that if you try to multiply the single weight by the single input for the single gate, the result is going to be off by some margin. One might say that if the margin is like 0.01 or 0.001, it's not much. Problem is with RNN that they accumulate and they also sum, and sometimes they multiply with each other. You see, there are so many multiplications here. The problem here was that doing that kind of multiplication, the output was like 43 instead of 58, which is really off by a lot. It's off by 15. So I didn't really get the real result. The solution was basically nothing more than, let's see if it's here. Yeah, was multiplying using the actual multiplication by the whole number, by the whole matrix. So, well, that's just a note to remember. It's really important to remember that if you try to reproduce the results manually, let's say with the weights, you might encounter these kind of issues. So the reason why we are all here gathered, the weight dynamics, the weight evolution over time. So as I said before, in the beginning, I was saying that after epoch 1000, let's say 1500, you see that the loss is disappears. It merges with the x-axis. So one might say that it's not really useful. Let me drink some tea. Sorry. One might say that it's not really useful anymore to train. Nothing farther from truth, because as you see here, after epoch 100 and 500, which is here more or less, the weights keep changing, and you see here the magnitude of the reset weight 0 is larger than the magnitude of reset weight 1. At the end of the training, they are really in the opposite situation, almost. So, or even more, actually, it's the double. So here they have like this distance. This is really small. At the end, they have this difference in magnitude, not distance. Let's talk properly. And you see here is this is really important. Another thing, how they are symmetrical. So I love symmetries, and in this case, the symmetry is astounding. I love it. You see that at the beginning this grows and this goes down, and at some point they almost at the same point at the same time they decide to change their direction. Also, note one really important thing. I noted these three lines: epoch 100, 500, and 750. And that's because these are the points where the training at their they best, how to say, they change it a lot in this point. So here it's 100, so this plateaus. This starts again to learn at 500 and stops again to learn like around 750. So that's why. And at this point, you actually see this change. So you see here, well, at the beginning, it's not really. Well, you see here, there is a peak, so around 150. It's not really 100, but it makes sense, anyways. Here you see that at this point, the function starts to change direction. And here, instead, it was going up and it goes more up. So it's like a saddle point here, and it starts going even farther up. And at this point, it starts going down. So the change in weight follows a lot the training loss curve. And this is really nice. And again, 150 here is where they overlap, so where they are the same. And the same means that they have value 0 0.6 almost. And one more thing we need to keep in mind is that these are the reset weights. So, how to say, these are the weights that are put on the reset gate. So these weights tell the network how much they should reset based on the input from the 0 data, that is the number, and 1, which is the flag. So The resin shouldn't reset much by the value, and this is actually pictured here. So you see that the weight put on the value is 0. I don't know 25, so it's not much. The reset gauge puts more value on the flag. The flag might be 0 or 1. So in that case, if it was 0, it wasn't really a signal. And maybe in the training, before training, we should have add some different flag for the negative case. So like -1. I don't know. It's too late now. But yeah, it's really nice to see this. So let's go to the next wait, which is the update gate. And again, we see here. Let's see if I can make it. All right. We see some really important uh, kind of not really a symmetry here, even though we don't see a real symmetry in this between these two lines here. We see a symmetry on the other hand between this and this. You see, they or even with this. You see, they follow the same. They are like mirrors. It's like you put the mirror here, and they are a mountain and the lake that reflects the mountain. So they do the same. And in this case, the update weight puts a lot of weight on the value and really small, actually negative value on the flag. So, but it's really strong. So it actually means in this specific case that we don't have to see that. I mean, it shouldn't be positive. It doesn't need to be positive. It can be just large, and then be kind of. There could be a counterpart by another weight, another negative weight that cancel the sign, and it becomes like a square of 3, sorry, square of 3, which is 9. So I don't know, but anyways, this difference is the largest, I believe, yes. And also again, after epoch 100 and 500, the weights don't stop changing. They change, and they change a lot. So the 100 and 500 is here, and they are like 1.2 apart from each other. At the end, they are like 2.5, so they double the difference in magnitude. So it's really important again. I guess this is my favorite plot. This is perfect symmetry. I love it. Again, don't mind before the 100 epoch. This is where the first learn. This is random, so we shouldn't look at this. This is where the first last drop happens. So this is what we should see. And again, around the 750 50th epoch, we see some sudden change at some point. Sometimes before, sometimes a bit later, sometimes a lot later. Sometimes this doesn't just goes down, and you see here goes down again, and again here something happens in the epoch 750. And again, let's see the training loss of the epoch 750, which is here. Yes. So here, this is where this happens. So this is where this happens. So it's really nice to see this. It's showing that probably the network was trying to do something else, was trying to find another way to solve the problem, and at some point it just found another another steepest descent, and it just followed through. And you see here, you see it here again, you see it here again. Maybe this was the starting point. So this weight started the new descent, and then this followed first, and then this followed after, or the opposite. But this is really nice to see. And again, this is the weight put on the new gate, on the new value. And again, this is negative, this is negative. So when they multiply to each other, they just cancel the signs. Okay, so let's go to the hidden reset gate. So this is the reset gate that happens on the hidden unit. And also here, wait, just to be on the same page, I will show you something. This. So far we have seen, where was it? Up here, yes. So far we have seen these three weights. Now we see these three weights. So UZ, UR, and UH. Well, actually it's UR, UZ, and UH in order down, but below. But so they happen on the same, how to say, they happen on the hidden layer. So they happen on the same level, but on a different layer. So this is the information coming from the previous, iteration. So at the first iteration, we just initialize it with 0, and then we just let the hidden layer evolve following this. So basically, again, we reset some data from the. We decide here how much to reset. We decide here how much to update. And here we decide, we propose a new candidate for the hidden layer. And then we say the new hidden layer, how much should be of the candidate and how much of the previous value. So don't forget about the old value. Add something to it, how much it's decided by ZT. So this is the meaning of the update gate. It says how much should I consider the new candidate for hidden unit, and how much of the old information should I keep. And the candidate again is it's given by, it's a multiplication. Here is a Hanuman product. I don't know if I said it here. No, but anyway, it's a Hardeman product, meaning that it's an element-wise multiplication, meaning that basically you multiply element by element the two matrices or two arrays in my case. So basically you say, all right, so this is the old hidden layer. How much should I reset? How much should I forget about it? And why do we say forget about it? Because this R says basically it's, you see, it's an addition to the to this other term, so it's a bit different, but still it says how much should I, if I directly multiply this weight, which is this actually. So this is a sigmoid, so this it's between 0 and 1. So basically it says how much should I reset about the whole state, because this is between 0 and 1. So this cannot be, it's really hard that this is 1 or all the values of the hidden layer are 1. So it's going to be like 0.5, 0.3. And this, for example, let's see one example. For example, here, So R1, for example, in my case was 0.81. So this meant you should forget zero point 0.2. So you should keep zero point 0.8 of the old value. In this second example, it said you should remember 0.89 of the old of the previous gate. You see here. In fact, at the beginning, I had 0.11. No, this is not a good example, but yeah, it's a good example actually. So 0.11, and after the reset gate, after the update rule, or actually here, it becomes the candidate is minus 0.001. So when you add it using this z parameter, at the end you obtain this, right? So again, reset 0.81, and in the last step reset was 0.89. So they are really high. So this says how much should I keep of the old memory. And again, this makes a lot of sense. Since we are adding stuff, so we actually want to keep memory of what we had in the past. This is not going to be one for some reason. Maybe it's a clipping of the gradients. I have no idea. But this makes a lot of sense, really a lot. And also the weights of the reset gate, which are the first we saw here. This we could have, this is something I can add to this article that I will probably add later on. But like, see how the reset gate was at this stage of the training. I have all the weights, so I can do that if I want, and I will try. But let's try to finish this analysis. It's important to complete. So again, reset in the hidden, from the hidden layer. This is nice. It's nearly 0.25, 0.1. So it says actually, we can say probably that this means forget everything. No, it's not true. It just multiplies all the hidden layers. So yeah, it might be so actually. So yeah, I could say just forget about the old hidden layer. Let's add the new stuff. Yeah, or maybe here is minus 0.12. The other one is 0 here, so it's 0.1. So this actually has some nice symmetry. So in this case it's 0.2, like, yeah, 0.2, whereas here it's minus 0.1, or yes, minus 0.1. So it's kind of symmetric. Again, let's see the formula. One random one is fine here. So no, here. So basically this is 0.25, and this is minus 0.15. So basically here is the sum. It's quite kind of an equilibrated sum of these two values. So this takes the let me see one thing. Oh, right. This is cool. This is really cool. This is a 1 by 2 times 2 by 1 transposed. So it becomes a 1 per 1 value plus 1 plus 1. So this is like the sum of three numbers, and you obtain this. I don't remember now the bias if I plot it. I really hope so, because now I wanted to show something about that. I didn't. This is really too bad. Science, maybe I plotted it here and we can steal something from here. No, I didn't. Really, this is really bad. because we saw that basically we have a really small amount of the input, a really small amount of the old value. It's like divided by 4. It's because it's 0.25, and this makes could make sense. No, it doesn't. No, I was saying something stupid, but yeah. So let's try to complete. Um, so what was I talking about? Yes. So this goes there. This is the update gate again. This is minus point. This was really large, minus 0.18, but then it just went really crazy up to 0 minus 0.9, and the hidden new gate just stayed the same. So this was the most, I guess, most normal weight in the whole network. The linear, this is nice. This is really nice because this follows really. I wouldn't say precisely, but it really follows a lot the training and validation loss, and it goes up to minus zero point 0.4. And this makes actually a lot of sense. We said before that the weight, the update gate, was it? Yes, is minus point. No, it wasn't this one. It was the reset gate. Yes, minus 2.5. All right. This says how much should I keep of the old of the new input in the new hidden layer. So 0.25 here, around 2.25, and this goes to 4. And if you multiply them, you obtain 1. And this is nice because at the beginning I normalize all the input values to 1. So if they are the maximum value is 100, I divide by 100 so that I have more stable data to train with. And this linear layer makes a lot of sense. This means that, all right, let's just use small values during the elaboration of the gated recurrent unit. Let's not let not explode the gradients. We could easily saturate the sigmoid with large values. In this case, we don't, because we're trying to keep the numbers small, like with small constants. But at the end, when we don't have any more fear of the saturation of the gradients of the sigmoid, of the activation function, we don't care anymore, and we just multiply by 4 and we get back our result. And again, this makes a lot of sense. So thank you for staying with me during this. I will publish this article as soon as possible, and this video will be in the article itself. This was easier for me to talk about it, so that I can then maybe also transcribe it and put it a bit more in a nicer way, maybe add some more information to it. But yeah, so thanks for watching, and bye bye.